Things start to get a little bit more complicated when we begin putting substituents on a cyclohexane ring. So notice that in chair 1, the methyl group that we have here is pointing straight up. So this is an axial position. And when this flips to chair 2, the methyl group takes the equatorial position. When the methyl group is in the axial position, if you were to draw a Newman projection of this, you would do the following. I would say if I'm looking down this carbon-carbon bond, I see a methyl group sticking up in the front. I see the rest of the ring that I'm just going to represent like this off to the left. That's here. I see a hydrogen off to the right. In the back, I see a piece to the ring here. And I see another hydrogen off to the right and another hydrogen down here. What you should notice is this. You end up with a gauche interaction between this carbon and this carbon. If we were to look down the bond this way, we could draw an identical Newman projection. So we'd come up with a second gauche interaction. However, when the methyl group shifts to the equatorial position and you take a look down that same carbon-carbon bond and begin drawing a Newman projection, what you'll notice is you get a different Newman projection. You have the methyl group off to the right. You have the hydrogen that's in my hand sticking straight down there, this one. This group here, the CH2, and I'm just going to put R to represent the rest of the ring, as here. In the back, I have sticking up a hydrogen off to the back right here, and then a CH2R group here. Notice this time there is no gauche interaction taking place. And if you were to look down the carbon-carbon bond this way, you would see that there again is no gauche interaction. So by having the substituent in the equatorial position, you are able to alleviate the gauche interactions, which of course is a type of steric interaction. So there's an energy gap here. Since we said that we could draw Newman projections looking down two different bonds and we would see two different gauche interactions when the atom is axial, each gauche interaction is, of course, if you remember, 3.8 kJs per mole, and you don't have those interactions here when it's in the equatorial position. So there's a total difference between these two chair forms of 7.6 kJs per mole. So this time, when the chair interconverts from chair 1 to chair 2, it turns out that chair 2 is the preferred form by 7.6 kilojoules per mole. Therefore, at equilibrium, you will have a 95:5 ratio of methyl group in the equatorial position to methyl group in the axial position. So it's heavily preferred at equilibrium to have that methyl group in the equatorial position. So as the R group, the substituent, starts to get larger, for example, here you have a T-butyl group, it cannot occupy the axial position. Not only are the gauche interactions becoming more and more predominant, but you also have issues going through the high energy boat conformation. And so with T-butyl cyclohexane, 100% of it at equilibrium will place the T-butyl group in the equatorial position.